Thank you, Vice President. It's a pleasure to be here. So what I want to do today is to give you an overview of some of the ideas that Richardson and I have been writing about for 30 years or so now about how culture relates to human evolution. And in particular, I want to convince you that of three things. I guess I have to get behind that. Okay, that's the right one. So by culture, I mean the fact that humans, unlike other animals, have the ability to accumulate information in populations over time. People learn from each other. Of course, other animals do that to some extent. But only humans have the capacity to learn things, change those things. The next generation learns them again. And after some time, you end up with tools, ideas, knowledge that no individual could invent or create on their own. And that's what I call cumulative cultural evolution. And I want to convince you of three claims. The first is that this is essential for what I call superadaptation. Modern humans exploded out of Africa something like 60,000 years ago. And ever since then, they've been astonishing evolutionary and ecological success. So much of the success of turning energy and matter into humans that we have to worry about the consequences for the globe. But nonetheless, just look around Toulouse or any other place in the world and you'll see a planet dominated by human ecology. And the second thing I want to convince you of is that cumulative cultural evolution that leads to such an explosion in adaptive capacity demands that people, or any creature that has the same capacities, have a psychology which motivates them to learn things that other people are doing, to adopt behaviors, ideas, knowledge that other people around them have, even when it conflicts with what their reason or environmental cues or other direct informational assets they have. And so that's a consequence, a requirement of the cumulative adaptation I want to claim. And it has a side effect, which is that it causes us to do a large number of peculiar things that you'd never catch a baboon doing. Climbing mountains, for example. No sensible baboon would go hang out on the top of a cold, scary, dangerous place, and yet Chamonix and Yosemite Valley and places like that are full of people who do exactly that. So, and we do many other things, of which I'll give you a few examples, much more maladaptive things than rock climbing. So, go ahead. Okay, so let's turn to the first claim. This is a composite satellite photograph of the world. So what the world looks like at night, and it shows where the lights are on. But if an extraterrestrial anthropologist or biologist had arrived at the Earth 12,000 years ago, when all humans lived by hunting and gathering, there was no farming, no cities, none of the things we think of as modern human adaptations, and taken a composite photograph where the hunter-gatherer campfires were at light at night, it would look more or less the same. By 12,000 years ago, humans had spread across the entire globe except for Antarctica and a few remote islands, Iceland and some of the Pacific Islands. And that only took a few thousand more years. So humans spread across the entire globe in 60,000 years. And this is an extraordinary fact that we don't make enough out of. So to see what this means, let's compare the human range to the range of other mammals. Terrestrial mammals. I'm going to stick with terrestrial. It's hard to compare humans to or anything to marine animals. But anyway, okay, so this is a map of this is a map of the geographical ranges of our neighbors, the other apes. So here are chimpanzees in brown, gorillas in yellow, orangutans in pink, and gibbons would be the red, and also where the orangutans are. So these are all the other apes. And you'll notice that the ranges are quite restricted. Typically, it's a particular habitat, a range of habitats. So orangutans, it's deep tropical forest. Chimps are a little wider ranging. They can live in dry forest or tropical forest. This is all the chimps, bonobos and chimps. And they're geographically restricted. So there are no chimpanzees in South America, for example, even though there's plenty of tropical ranges. This is typical for mammals. Relatively narrow range of habitats and geographical restriction. The mammals that have the widest ranges, leaving aside human commensals like Norway rat, are big predators. I think this is the range for wolves. The green is their current range. The red is where they used to live and don't live anymore because we pushed them out. And this is, I think, the biggest range of any mammal besides humans. And you can see it's most of northern Eurasia, most of North America, no wolves in South America, no wolves in Africa, and no wolves in Australia and New Guinea. Okay, so humans have a wider range than any other creature. And what that tells us is that humans are better at adapting to a wider range of environments than any other creature. And if we look at it in more detail, so big predators like wolves typically have one or two main modes of acquiring resources. They're either pursuit predators like wolves, they run their prey down, or they're stealthy ambush predators like puma in North America. Humans occupy this range from the Arctic to the tropical forest across the entire world, using an amazing range of prey items, tools, everything else. Now, I'm going to go into some detail into one habitat in just a bit, but the geographical range underestimates the ecological range of humans. And the reason this is important is that biologists, I think with some justice, accuse humans of being choosing criteria to judge themselves that make them look good. So, we only have stone buildings, no other animal has stone buildings, except maybe termites, and so on. But range is a standard zoological criteria, and humans have the biggest range of any creature. And we occupy this range extremely quickly. So, it doesn't show very well, but this is a map of what the world's habitats looked like 60,000 years ago when people moved out of Africa. You can see that the shorelines are somewhat different because sea levels were lower, and that the world's ecozones were quite different. So notice the tropical rainforest, you can't read this, but I'll tell you the tropical rainforest is limited to a tiny refuge in central Congo and some refuges in what's now Indonesia and Southeast Asia. Most of Eurasia is a dry desert, or up here there's a so-called mammoth steppe, a dry, cold grassland covered with hairy rhinoceroses and hairy elephants. So humans left Africa about 60,000 years ago. It probably originated, modern humans probably originated down here a few tens of thousands of years earlier. We're not exactly sure. And then they raced across the globe in ways that are completely unparalleled in biogeography. So there's good archaeological data. We know that the escape from Africa data is mainly genetic, but there's good archaeological data that people reached Australia and New Guinea 50,000 years ago. And in doing so, they had to cross 90 kilometers of blue water, open water, a feat that only one other terrestrial mammal species had managed in 65 million years. So 65 million years ago, the Death Star comes along, all the dinosaurs die, we get mammals, and at that time, this Australian guinea was separated from the rest of the world. Marsupials evolved here, placental mammals evolved here, and only one placental mammal got across, it's a species of rat, got across in 65 million years. 10,000 years after people left Africa, they crossed the barrier and soon occupied all of the Australian Guinea continent. By 40,000 years, people were living at the latitude of Moscow on the Mammoth Steppe, also in southern France, here in Toulouse, 40,000 years ago. And by 30,000 years ago, people were living north of the Arctic Circle, 73 degrees north. There's a site there where the Yana River flows into the Arctic Ocean. And this is an amazing rate of adaptation. So in 10,000 years, people transformed themselves from tropical foragers into dry country tropical foragers into all these other 10,000 years, into being able to make a living in a wide variety of other habitats in a way that no other organism has ever done. So how do they do this? The standard answer is, we're just smarter than other creatures. Is Yogi there a character that people know about? No? No. So this is a character on American cartoons that I grew up with and still available on the Cartoon Network in the US. And he was fond of saying, he's the kind of dumb guy. And he's fond of saying, I'm smarter than the average bear. So the point is that the standard answer, all through physical anthropology and many other disciplines, is that people are cleverer than other creatures. And that's what allows them to solve problems and adapt to a wider range of circumstances. And just to show you I'm not making this up, I'll make fun of Steve Pinker here. This is the New Yorker version of Steve Pinker. And for those of you, I mean, he must be known by almost everyone, but he's a famous, extremely prolific, extremely smart evolutionary psychologist. He writes, these inferences, which he means how people figure stuff out, are played out internally in mental models of the world governed by intuitive conceptions of physics, biology, psychology, including the psychology of animals. It allows humans to invent tools, traps, weapons, to extract poisons, drugs from other animals and plants. These cognitive stratagems are devised on the fly in endless combinations suitable to local ecology. They arise by mental design, are deployed, tested, and fine-tuned in the lifetimes of individuals. This is a very standard view. Now, I agree that humans are, in some sense, smarter than other animals, although comparing the cognitive abilities of different animals is always hard. But humans in the laboratory do seem to be better at causal reasoning, theory of mind, some tasks that we would think might help them be better at figuring out how to live in different environments. And our brain is extraordinarily large for our body size. That's some evidence. We're paying quite a high metabolic cost to carry this thing around. It must be good for something. Well, what I want to convince you of is that even though humans are probably smarter than other creatures, we're not nearly smart enough to solve the range of problems that are involved in that expansion we just solved. The expansion across the globe involves solving problems that are vastly beyond the capacities of individual learning and reasoning. And to convince you that, I'm sorry this is not as clear, it's a little bit of light on the screen, but I want to imagine a thought experiment. And the thought experiment is the following. I want to imagine a population of humans. Let's make it this population of humans sitting in the room. Smarter than average, for sure, right? You all agree? And we're going to maroon you on an Arctic beach, right there. And north of the Arctic Circle, we'll give you 6 months of beans, tools to stay alive, to learn stuff, and then we'll take away all of the products of civilization and your last can of beans. And we're going to ask, can you learn with your own cognition, your own learning resources, to live in this environment? If it were true that human intelligence is what's necessary, sufficient to learn how to live in different environments, you should be able to do it. You're smarter than other people. We've already established that. And this is not a ridiculous question, because this is the way other animals, to a large extent, adapt. Most animals arrive in the world with their genotype, they acquire information from the environment, and they've got to figure out how to make a living. There are a few animals, like chimpanzees, that have simple traditions. So chimpanzees use stone tools to crack open nuts in some populations in West Africa and not others. And there's a certain amount of circumstantial evidence that this is socially transmitted. But there's no evidence from any species of the cumulative evolution of new behaviors that individuals couldn't learn on their own. So the difference between humans and other creatures is, my argument is cumulative cultural evolution. And the question is, can we do without it? Okay. So we know that humans got to the Yana River at 73 degrees north, and we've marooned you at the same latitude. What will you need to live? And we don't know much about the Yana River people. We have some archaeology, and it doesn't tell us enough. But we know a lot about ethnographically known foragers from the rim of the Arctic Ocean, especially about Inuit and Eskimo peoples on the north coast of North America. So let's look at what they had to have in order to stay alive, stay fed, raise their children, and persist as populations. Well, first you're going to need warm clothing. The mean temperature in January at the Yana River or in the Central Arctic, where these people live, Central Arctic in North America, is about minus 25 degrees C. If humans die without clothing at the temperatures much below minus 1 degree C, you will die by hypothermia, no matter what. You have a few hours to live. So you need warm clothing. And the Inuit had spectacular clothes. And you're going to have to figure out how to make those if you're going to live on this Arctic beach. And there's a lot of hard problems to solve. So it seems likely that fur is the right answer. You're not going to find much fleece or cotton up there. But which animal? Polar bears, seals? The answer is caribou, what the Europeans call reindeer. Because reindeer have a special kind of fur that has air pockets in the fur, and it's exceptionally warm for its weight. Does it matter when you harvest the caribou? Turns out it does. Turns out that in some times of the year, caribou skins are full of holes, like from biting insects. Other times not. Okay, you've got a bloody pellet. You killed the caribou, you skinned it. How do you make that into something soft and supple that you can wear? You guys know? I do know, because I've read about it, that curing caribou is what you've got available up there. Caribou hides. How to cut the clothing. Turns out that's complicated. You need ventilation. Sweat is the enemy of warmth in cold places. You never want to get hot. Where are you going to get your thread? You need thread to sew these hides together. Where are you going to find that? Turns out the answer is along the backbones of caribou, the sinew make the best thread. Where are you going to find your needles? Turns out the stitchery of living in a very cold place with high winds, and sometimes you have to walk through water in the spring and fall. You need exceptionally well sealed garments. The Inuit had spectacularly well-designed garments, including stitches that were waterproof. Okay, that's just clothes. You're going to need to stay fed. You need caribou for your clothes. You need caribou in the fall because in between the time that the sea freezes over and it gets too cold to fish, you need to hunt caribou and you need a bow. But you have no decent wood to make bows out of. The only wood you have is driftwood that's flowed up the Mackenzie River and spread out across the north part of North America. It's spruce. It's a really crummy wood to make a bow out of. It's soft. It's not very dense. And the Inuit had spectacularly designed composite recurve bows that maximized the power. So hunting big animals, like caribou are a couple hundred kilos. You've got to kill an animal like that from 50 meters. You need a powerful bow. You have to figure out how to make one, and that's not easy. Clothes aren't enough. In the wintertime, you need shelter. In the central Inuit, they lived out on the sea ice in the wintertime hunting seals, these holes in the ice. They know how to make snow houses. Igloo is the word for house in Inuit, so you need to know how to make this kind of house. And you need a source of heat and light, because if you're living out on the sea ice, there's no running water. You need to melt ice to make water, otherwise you're going to die of thirst. You need heat to cook your meat. You can't live on uncooked meat very long. And the Inuit have these extremely clever lamps that were made out of carved soapstone, used steel fat, and wicks were made out of moss that you collect in the summertime. You have to remember to do that. And used all winter long to create water, to light and heat the houses. And it just goes on and on and on. Sorry, I should wave my mic hand around. This is a toggle harpoon. It's necessary for hunting large sea mammals. It's very bright in the summertime. To avoid snow blindness, you need goggles. This is a special kind of spear which is used to hunt fish in the springtime. And here are two of the big items I haven't talked much about, dog sleds and kayaks, both exceptionally complicated bits of technology. So what's the chance that you, as an individual, are going to be able to invent all these things and make a living on the planet? Are you going to make it? Well, I have to say, I don't like the chances. I think you're doomed. But this is a thought experiment. I've actually had people say to me, oh, I don't think so. I think I can make it. So real experiments are the thought experiments. And this experiment has actually been run many times in the last couple of centuries. I call it the Lost European Explorer experiment. And the way it works usually is some intrepid Europeans go off someplace, things go wrong, and they either starve to death or die of cold or something, or if they're lucky, some local folks come out of the woodwork and keep them alive long enough to get back to civilization, such as it is. And there are many examples of this. Just let me give you one of them. This is Sir John Franklin. He left England around 1844, 45. He was trying to find a way across the north coast of North America. Several people had tried before and failed. This is the best equipped British Arctic expedition of his time. He had Arctic experience, 2 ships, a large crew, a large library, lots of tinned food, canned lemon juice to prevent scurvy. It was as good as science could do at the time. And the Franklin expedition sailed off into the Arctic and was never heard of again. At the time, it was a sensation. It would have been, on the front pages of the newspapers, the talk shows would have been discussing what happened to Sir John, etc. And this is a painting by a British painter named Edward Landseer. which is entitled "God, a Man Proposes, God Disposes," and it's Sir Edward's view of what happened to the Franklin expedition. It's sort of amusing, aside, that he was mainly known, aside from his painting, which is very famous and controversial, as the man who painted portraits of Queen Victoria's dogs. But anyway, something about the English monarchy and dogs. But, so we do know now from archaeological work what happened to the Franklin expedition. They wintered frozen in the ice near King William Island in 1846. A little bit north of there in the winter of 1845. They ran out of food. They got desperate. They started south, hoping to get overland to Hudson's Bay trading post, 1,000 miles south, and they died of starvation before they got there. And we know that because we found their remains in some diaries. Now, the thing is, the Inuit, the Netsilik Inuit, were living on King William Island. They've been living on King William Island for at least 700 years. No boat, no canned food, no nothing, doing just fine. In fact, the main harbor on King William Island in the local language is known as lots of fat. So if you had the right knowledge, this was a provident environment. The British people starved, the British sailors starved, not because they weren't smart enough, but because they didn't have access to the pool of information that had accumulated in Inuit populations over hundreds of years of living in this rather tough environment. Okay, so the key to human adaptation is that we can learn from each other. If the British sailors had been willing to learn from the Inuit, which they weren't, they probably would have survived. 60 years later, Roald Amundsen made the same trip, took an Inuit dictionary with him, made an effort to learn from the Inuit, and, at least according to his biographer, gained weight. He was a rather difficult guy, so you don't know how much is fiction, but he definitely made it with his whole crew in a very small boat. Okay, so jokes aside, it's fine as an approximate short-term sense to say if the British sailors had been able to learn from Inuit, they would have been able to make a living and stay alive. But the question is, what is it about a population of individuals learning from each other that makes, over time, it makes that process more likely to generate complex adaptations that individuals on their own can't invent? And I think this is not as easy a question as people think it is. The standard answer is that knowledge is what economists call a non-rival good. I can learn something, and then if I teach it to you, it doesn't decrease the value to me very much or at all. And as a consequence, when we can learn from each other, the ability to imitate spreads the cost of innovation over many individuals. And I think this is surely true. But as we'll see in a second, it's not sufficient to understand, I don't think, the essence of why cultural evolution is adaptive. So that brings me to the second claim I want to defend, which is that the cumulative cultural adaptation, like we've seen kayaks, toggle harpoons, all this stuff, requires people to ignore. I put reason in quotes. What I mean is the evidence that their individual cognition and learning efforts do. It'll often have to be the case that what they can get out of the environment will say to one thing. If people are doing something different, they have to do that in order for cumulative cultural adaptation to work. Well, let me see if I can convince you that. Okay, so to do that, I'm going to do the closest thing. No math, I promise, but but I want to, I'll give us a graphical picture of a very simple, rather famous model in the field. So this is a kind of toy model. It boils a very complex reality to a very simple process. But bear with me. Let's see if we can understand the simple model first, and then I'll wave my arms rapidly and tell you that it applies to more complicated situations. So I want to imagine there's two types of people in the world. There are people who imitate. They pick a random person from the previous environment and copy them. And there are people who are reasoning people. They go to the environment, they gather information, and they try to figure out what the best thing to do is. And to keep things especially simple, let's assume that the learners, the second type, always get the right answer. So the environment's varying, they're trying to figure out what the right thing to do is. Learners always get the right answer, but they pay a cost. Okay, so what's on the horizontal axis here is the fraction of the population that are learners. I'm sorry, that are imitators. And so 1 minus that's the fraction that are learners. And the vertical axis is some measure of payoff. Okay, so survivorship, body weight, something that people like. And so let's just call it fitness. So the fitness of learners is constant. They get the right answer, less the cost of learning. Doesn't matter what the imitators are doing. The fitness of imitators depends on the frequency of imitators. When imitators are rare, they almost always get the right answer because they're almost always imitating a learner who's got the right answer. If there's one imitator and 10,000 learners and the environment hasn't changed, they're going to get the right answer. But as imitators become more common, some imitators are imitating imitators who are imitating imitators, and somewhere back there, the environment changed. So as the frequency of imitators increases, whoops, oh well, sorry about that. As the frequency of imitators increases, the connection between the population and the current state of the environment gets weaker, because it's learners that are gathering information about the environment, and then imitators are taking advantage of that. So if we imagine that the frequency of the two types depends on their payoff, so it's a fitness, then it's real easy to see what's going to happen. The equilibrium is going to occur where both types have the same fitness. Otherwise, if they don't have the same fitness, one type's going to increase. And that means there's an equilibrium where both types are present. And this is the way I've drawn it. Lots of imitators and only a few learners. That turns out to be pretty common in this model, but it all depends on the parameters. Now, here's the thing. Notice that at this equilibrium, the population has the same fitness as a population with no imitators. So imitation has evolved already, but it hasn't done anything for the ability of the population to adapt to the environment. Now, why is this? How can we understand this? Well, I think this picture will give you a clear understanding. This fellow here is an imitator. This person here may or may not be an imitator, but she is being imitated. So imitators are scroungers. They're absorbing the value that's created by the efforts of learning. So imitators aren't contributing anything to the average fitness of the population. So as their frequency increases, the behavior of the population tracks the environment less well. It's true that we're paying less learning costs. We're spreading the learning costs over more individuals, just like the standard answer says. But fewer and fewer people are learning until we reach an equilibrium where where the average fitness of the two types is the same. And so with this way of thinking, I will tell you that this result is called Rogers' paradox. After Alan Rogers published the paper in 1988. And it's a subject of quite a bit of research nowadays. Lots of people, including at least one person in this room, has worked on this topic. And I think that it's fair to say that things are complicated, as always, but a fairly wide range of models will generate this result. It doesn't depend on the very special, simple assumptions that I've told you. And what it points out is that what you need in order to get the average fitness of the population increased, it has to be true that increasing the number of imitators, allowing populations to imitate, has to somehow make more information available to the population. In particular, one way to do that is by making individual learning either more accurate or cheaper or something. Now we have an equilibrium at which both types are present, but the average fitness is higher than it was back here where there was no imitation. Okay, so how can this happen? This is very abstract. As I said, there's been a bunch of recent research and things are complicated, but there's at least two ways that it can happen. So one thing that imitation can do that makes learning better is it allows individuals to learn selectively. So the world presents people and all kinds of creatures with evidence. Sometimes it's great evidence. Sometimes you see, for example, Kalahari and Bushman know that porcupines are monogamous. Porcupines are nocturnal, they're very shy, they're hard to see. How do you learn this? Well, in special circumstances, you may live near a burrow and see the same pair for year after year, or other kinds of evidence. So some lucky event may provide strong evidence that this fact is correct. Lots of other people who don't see a porcupine once in their life, or twice in their life, or only at the end of a spear, would find this much more difficult for them. So when the value of individual information varies, and when individuals can evaluate the merit of the evidence they've got, an imitator can learn when the evidence is strong and copy somebody else when they're not sure. This is kind of the way science works, right? We have p-values. If p is equal to greater than 0.05, we say, yes, we learned something new. Less than 0.05, but otherwise we just keep believing the thing we believed before. Okay, so the other way is that imitation can allow the accumulation of small improvements. So lots of complicated objects like bows and kayaks have many dimensions, and they vary continuously. You know, how long do you make the bow, how thick do you make it, what kind of sinew do you put in the back, how do you glue the sinew to the bow, etc., etc., etc. Small, random trial and error changes are more likely to be improvements if the bow isn't already perfect than big changes, for the same reason that small, random mutations are more likely to lead to an improvement in fitness than big mutations of large effect. This is one of R.A. Fisher's great insights. In some ways, Darwin's as well. And so the same thing is true of learning. And so if small steps are easier and cheaper and more likely to be adaptive than big steps, then by accumulating, somebody makes a bow, somebody else makes it a little longer, somebody else figures out that it's better if it's a little thinner, and gradually over generations, these small changes, many of the changes that people make, of course, are bad, and they don't get preserved, but the good ones get preserved, and over time, adaptations arise that no individual would have the time or energy or resources to do all the experimental work necessary to do that on their own. Okay, now notice that both of these mechanisms require individuals to ignore reason some of the time. So take the first one. Everybody's getting evidence from the environment. A lot of people are getting evidence that one thing is better, but it's not strong enough evidence, and they keep doing what everybody else is doing. That's what's required to make the model work. Same thing is true here. If my psychology says don't meddle too much, do pretty much what other people do. You can make small bricolage kind of improvements, but not big ones. So mainly, I'm doing what other people are doing and only making marginal improvements. that's another kind of thing that it says that I'm mainly influenced by what people around me are doing. Okay. So that's the kind of theoretical part of the talk. I'm going to turn to some more colorful examples. So my claim is that this psychology that leads to cumulative adaptation means that people have to be intrinsically motivated to do what other people around them do. And this psychology, I'm claiming, can be an adaptation. It can be something that's highly adaptive for people and for the species. So, and the benefit is we get by learning selectively, by accumulating small changes, we get, a population gets information at a low cost, and individuals get information at a low cost. And so we've had all these examples. Clothes, kayaks, dog sleds, toggle harpoons, fancy clothes, etc. All those things that an Inuit boy or girl growing up can easily learn, but would take way more of an individual's lifetime to invent. But this comes with a trade-off. The Inuit boy or girl has to pretty much do what other people around them are doing. They can't afford to spend all the effort that would be necessary to jump to the, if this happens to be the wrong answer, to the right answer. So this is a trade-off, and my claim is that it's an intrinsic trade-off of cultural adaptation. Just like the cube-square trade-off is a trade-off in morphological adaptation. The animals get bigger, their bodies get heavier compared to their bones, and that's something that evolution has to deal with. My claim is that's the same for cultural adaptation. And as a result, because people are intrinsically motivated to do what other people in the population around them are doing, if people around them are doing stupid things, or weird things, or things that you wouldn't catch a baboon doing, they're going to adopt those because that's what their psychology tells them to do. On average, that's a great thing. It's made us a tremendous success. But in particular domains, in particular places, in particular times, it can lead to many peculiar behaviors. So let's give some examples. That's fun, huh? Okay, so one of the things is that our cognition is not a blank slate. People are not a blank slate. Our cognition is specialized for all kinds of purposes. And when cultural transmission takes the biases that are built into our cognition and repeats them over and over and over again through the many generations of transmission, very weak biases can have big effects on the outcome. And so let me show you an experiment here by Tom Griffiths and his collaborator, whose first name I don't know. This is the famous guy, the professor. And he's done many experiments at this same time, so-called transmission chain experiments. So he starts people with some information about the environment. And so in this case, it's people get a bunch of XY pairs. So you're sitting at a computer terminal, you get an X number and you get a Y number, and you get 100 trials, 200 trials, and you're asked to learn the pattern. So in this case, the pattern is a parabola. Okay, so this is just one example. This is one person, the trials they got. I think this case was 50 data points they got. And then, experimenter / tormentor gives you X values and asks you to tell them what the right Y value is from what they just learned. So here's the results from one particular subject, fortunately anonymous. So not very good, right? Kind of, you know, but obviously a problem. So people aren't very good at learning this test, the hard test. But now here's the trick. So we now take the output of the first guy, and we use that to train the next guy. So this is like telephone, or people call that in French, there's a bunch of names. Okay. Okay, so now we use this as the training set, and we show 50 values to some poor subject, and we ask them to replicate it. And here's the result. Then we use that as the training set for the next guy, and You ask them to learn it, and here's the result, and you can see what's going to happen. After 4 generations, what started out in the world as a parabola is a straight line with a positive slope. Now, I picked this example because it's the fastest. Other starting points take longer to evolve, but no matter what starting point you start out at, no matter what rule you ask people to learn, they learn this after 10 or 20 generations. So it takes the longest if you give them a negative slope in a straight line. That takes like 20 generations. But after 20 generations, this is what you'll see. There's a lot of other evidence from cognitive psychology that people have a cognitive preference. If you're a Bayesian, they have a prior that relationships are positive straight line relationships. And it's not very strong in one generation of learning. But culture acts like an amplifier to take these small biases and turn them into striking patterns that have got nothing to do with the input. Okay, that's a laboratory experiment, but this kind of thing is probably very important in cultural evolution more generally. Just to give you an example, Pascal Boyer, a cognitive anthropologist who used to be at Washington University in St. Louis. I guess he's returned here to his homeland. And he wrote a very interesting book called Religion Explained, in which he attempts to use this exact same kind of reasoning to explain people's beliefs in supernatural agents. So there are no supernatural agents, I hope you'll agree. So I don't think there are any. And Boyer has a quite interesting story about how a combination of cognitive biases, a bias in favor of memorable, what he calls minimally counterintuitive stories, a bias in favor of explanations of the world that involve conscious, goal-seeking agents, some other biases, can explain many of the patterns we see around the world, cross-culturally, in beliefs about supernatural agents. Ghosts, gods, demons, etc. I recommend this book to you because it gives you an example of how you can take this kind of argument and generate very interesting testable hypotheses about things that people care about. Okay, but there are a lot of other reasons besides cognitive biases. So people's cognition should have been designed in lots of ways to not just to be have biases in favor of it, that makes them predisposed to acquire certain contents, but also biases that predispose them to learn things from certain people, certain kinds of people. So let me give you an example of that. There are good reasons to think that imitating successful people is a good idea. It's actually another way to solve Rogers' paradox. If you can measure success and you can preferentially imitate people who are successful, then that's a good thing to do. The problem is that what success in one environment may be different than what success in another environment. It would be hard for evolution to give us a rule that would tell us who to imitate in Toulouse and in Metzili. What makes you a success in one place is quite different than what makes you a success in the other place. And so, one good rule of thumb is you should imitate people who other people are imitating. And you can make that cogent, but the idea is pretty easy to see. If some people have actual information about what's good, then by following people that other people follow, you can get, that's a cue that lets you choose who you. The problem is it also can lead to kind of an unstable runaway process in which prestige systems go off in weird ways and end up doing things that aren't all that sensible, and here's an example. So this is the late Wolf Gulick, who's climbing a climb in Yosemite Valley called Separate Reality. This is 511D. Are there any climbers in the room? Nobody? What grade is that in French?
Oh, in French, it's
B12, okay. So the point is it's very hard. And what you should notice is no rope. So if he falls, he dies. And why is he doing this? As I said, no sensible baboon would do something like this unless there was a fig at the end of this crack. He's doing it because that's the way to get prestige in a particular community. And he traveled all the way from Germany to Camp Forest to take advantage of this. And this is a very cool thing to do. And people imitate him, and they imitate what he thinks is cool, and they try to do even better, and the whole thing runs away. It's a good general rule that leads to odd behaviors. I have to say, a lot of my evolutionary psychology friends say, oh, it's just sexual selection. He's just showing off for the girls. Now, no one who was in Yosemite Valley in the 1980s when he did this, or 70s actually, would think that was true, because there were no girls there. I know that. Experience, or almost none. But there's better evidence in my remembrances, which is sexual selection is something you should see sexual dimorphism, and women do exactly the same thing. They're caught up in the same prestige system. This is Steph Davis doing a climb called An Incredible Hand Crack in Indian Creek. This is 510D, not quite so hard, but still plenty hard. And she's not wearing a rope either. If she falls, she dies. Okay, this is a really stupid thing to do. It's not nearly as stupid as the prestige system that most of us are coming to. So this fellow here, like most of you, like most people who live in modern industrialized societies, commands resources. He would make Louis XIV green with envy. I left Albuquerque the day before yesterday. Got in an airplane, flew across the world like a god, right? And was here in perfect comfort. Louis XIV would love that. Now, that was paid for by IAST, but I could afford to pay for it too. And this guy has only had 2 kids. And that's a biological paradox. How could individuals who have access to fantastic resources not turn them into kids? That's what animals do. And the answer is that he's caught up in a prestige system that places value on impressing all of you and publishing a lot of papers, and he wants his kids to have the same kind of success, so he can only afford to do it. It's mad from an evolutionary point of view, but it's a consequence of being predisposed to value. I mean, I can say this as an outsider and say that I'm crazy, and I still value my success as an academic because that's the way my brain works. Okay, one more example. So another aspect of cultural adaptation is it's much faster than genetic adaptation. And it's probably much faster in proportion to the migration of people between different groups. Now, systems of repeated interaction in social groups, which are true of almost all social mammals. Mammals can remember individuals, at least in primates for sure, they can remember individuals. They can condition current behavior and past behavior. They can have norms which say people around here have to do X, and if they don't do X, they get punished, and if they do X, they get rewarded. And that's a recipe for generating many possible dynamic equilibrium, many evolutionary equilibrium. We can all insist that you give your property to your oldest son or your youngest son. We can insist that you have to marry your cousins or you mustn't marry your cousins. It can go on and on and on. And the great value of 20th century anthropology is to document the immense range of social arrangements which people have, often different in very small spatial scales. People 1 kilometer up a river and you begin to speak a different language than people 1 kilometer down the river. And that's a recipe for generating variation between groups if the rate at which adaptation, people's learning to do what we do around here, is fast compared to the rate at which people move from one place to the other. So the prediction would be that increasing the rate of adaptation will increase the amount of variation in normative behavior, beliefs about right and wrong, conventions between groups, compared to what we see in genetic variation. And this is data collected by Adrian Bell and his co-workers, and it compares cultural and genetic variation between groups, nations, in the world today. So the red, so I should tell you, the horizontal axis is a measure of how much variation is within populations and how much variation is between populations. So at this end, all the populations are more or less the same. They've got a lot of variation inside them. Here, if it went all the way to 1, every big population would be identical within and different between. And these numbers are typical for, it's called FST, these FST values. This is the frequency distribution of FST values from Cavalli-Sforza et al.'s big volume on classical marker variation. And you can see the FST values at the national level are very small. They're down below 5%. Adrian Bell calculated the same statistic for stated values in the World Value Survey. And what you can see is something like 10 to 20 times bigger. So what that tells you is there's a lot more variation between groups for things that are transmitted culturally than things that are transmitted genetically. And groups compete just like people, so this can lead to the spread of norms that increase the success of groups in competition. So let me just give you one example of that, a possible example. So this is my former student, Sarah Matthews, who did a fantastic study of warfare amongst the Turkana, who are a group of pastoralists in northern Kenya. She interviewed warriors, 120-something warriors, about their latest raid. People amongst the Turkana participate in raids about once a year. So men participate in raids about once a year. So a man might engage in 20 or 25 raids during his, they start when they're about 20 and they finish when they're mid-50s. And what this distribution gives you is the size of war parties. So what you should notice is this is a fraction of war parties that are a certain size. So the big number is 1,000, this is 0, the median is about 300. So these are groups of men that are going off in groups of size 300. These are people not all from the same village. There actually aren't villages. There's no political system. There are no leaders. There are no chiefs. There's no coercive authority. This is done voluntarily. And of course, there are opportunities for free riding. When the shooting starts, you can hide behind a tree. When you run away, you can take more than your share of loot. On the way out, you can decide, my stomach hurts. I don't think I'm going to make it to the battle today. And so there are lots of opportunities for free riding. And the fact that people do this is a big puzzle. They're not related. And it must have to do, and Sarah has convincing data, that it has to do with a system of informally enforced rewards and punishments. So the kind of men who are free riders or cowards or who cheat on the distribution of resources get punished. We know that for sure. And there's also lots of circumstantial evidence that people that get a reputation for not being a coward and for being a fair guy get rewarded in various ways, including by better offers of marriage. Okay. So here's the main fact I want to show you. So here's evidence of punishment. This is a guy. The punishment takes the form of being tied to a tree and beaten. This guy, you can't really see it well, but he's got huge scars from his beating 10 years ago. So, there are many possible norms we could have. We could have norms that say your own cows and the cows of your neighbors are not to be stolen, but the cows of other people nearby can be stolen. We could have a rule that says the cows of your clan's members are sacred, but the cows of other clan members are for brave men to steal. Or we could have a rule that says the cows of the Turkana are forbidden, but the cows of other groups are to steal. And the question, these are all norms. They can all be enforced by punishment, The question is, which norm do we enforce? And the answer is, it's the Turkana in this sense. So she did a vignette study where she told people stories about a group of men who went out and stole cows from another group of people. And in one case, it was another Turkana territorial section, about 100 kilometers in one direction. In the other case, it was a group of Toposa, a different ethnic group in the other direction. Otherwise, the stories were exactly the same. And she asked the sample of Turkana, what do you think about these guys? Is what they did wrong? Do they displease you? Would you criticize them? Would you punish them? The red bars are what happens when they raid another Turkana. There are 500,000 Turkana. Basically, that's a terrible thing. If you raid the other guys, there's no disapproval whatsoever. So this is a norm which is group beneficial at the level of the Turkana society, at the level of the ethnic group, which is also the level of cultural variation, which is what you predict based on a model of competition between culturally different groups. Okay. So I think this has been going on for a long time. The evidence is that humans have been cultural organisms for at least 100,000 years, and probably 200,000 or 300,000 years. And so that's a long enough time that if it leads to changes in the social environment, leads to ethnic groups, leads to cooperation on larger scales, leads to religion, and so on, then there's been a long enough time for those social environments to impose ordinary natural selection on the organisms living in those societies. And one of the best examples is here on the screen. So this is chimpanzee, and this is the human. And what you should notice is that the human has white sclera around their irises. The chimpanzee doesn't. And in fact, we're the only mammal that has a large white sclera around their eyes. There's one species of marmoset that has the lighter sclera. Marmosets are cooperative breeders, which is interesting. So all mammals have dark eyes, and humans have this white sclera. This is an adaptation. The back, this is the darkness around the irises is not there just by the construction of the eyeball. So the question is, why are humans different? And the answer I like is that it's been shown by psychologists that having a white sclera makes it much easier to detect direction of gaze. So it's much easier to tell which way a human is looking than a chimpanzee or your dog. And what that means is humans have been living in societies where it's a good thing for other people around you to know what you're planning to do next. And most other animals, all other animals, live in societies where it's a bad thing for other individuals around you to know what you're going to do next. So, despite the need of other animals to coordinate, their selection has shaped their behavior to make their behavior as unpredictable as possible, at least with regard to the morphology of eyes. And it's quite the opposite with people. And that suggests that people have been living in cooperative societies where it's beneficial to have other people know what you're going to do next long enough for this to change. I'm told that Svante Pabo is looking for the gene that causes this, and if he finds it, we'll be able to date it, and we'll know when people started being cooperative. Now, this is just an example. Human biology is full of adaptations, I think, that make sense in a cooperative world and not so much sense in an uncooperative world. It makes sense in a world of culturally shaped groups. So kids come into the world and there's a lot of evidence that they expect to find moral rules in place. And their job is to learn what the content of those rules are. Other animals, there's no evidence of third-party punishment, very little evidence of third-party punishment in other animals. People have shame. People punish themselves when they do something bad. They have moral outrage. They get furious when they see people, at least Americans do, when people make traffic violations called road rage. People seem to have, seem to be prepared to readily identify with large, symbolically marked groups, ethnic groups, football teams, you name it. People can get really agitated, really excited about a group that they couldn't possibly be related to. And this is true of simple societies as well as complex ones. So all of these things, I think, make sense as the consequence of a coevolution of social and cognitive and informational adaptations created by culture that then create new environments which favor new kinds of ordinary genetic adaptation. Okay. So my final slide, I'm often asked this question, does culture override biology? And Paul already telegraphed my answer about this, which is this is not the right question. Culture, the psychology that makes us cultural organisms, is an adaptation, just like our weird pelvis and the thick enamel on a mold. Now, it's an adaptation that is complex and creates novel trade-offs and novel behavior. It makes us exceptionally good at adapting to a wide range of environments. But it also makes us predisposed to do peculiar things, like rock climbing and publishing academic papers. So the real questions, the scientific questions are, how does it all work? I've told you a story. Quite a bit of the story might be false, in the sense that the examples I've given you were still in early days. But the basic idea that our psychology has been created by natural selection, that must be true. You can't socialize a chimpanzee and make it into a human. It just won't work. We're different. Our brains are different. Our resilience is different. And the scientific process is to figure out how that works. How do we learn exactly? This is something that both theorists and ethnographers and psychologists can work together on. And the idea that there's some struggle between culture and biology is just not the right way to think about it. Culture is part of human biology, and the right way is to find out how our genetic and cultural evolutionary processes work together. Thanks very much. Now shall I manage my own questions?
Yeah, well, this is